in ECE at UIUC under the advisement of Dr. Overby. He recently returned from Boston, where he was focused on growing his startup company, OSO Technologies. Trevor is back to finish his PhD work under Dr. Overby, concentrating on how to protect the electric grid from high-altitude electromagnetic pulses. So we're grateful to have Trevor with us again.
All right, thank you, Chris. My name is Trevor Hutchins. I'm under the advisement of Dr. Overby, and I'm excited to be back here and work with all y'all again. So I kind of stepped in somewhat last minute on these slides, so they're a bit brief, but hopefully they'll be interesting enough. All right, so calculating geoelectric fields from real-time magnetometer data is the topic. Obviously. Okay, there we go. These were animated. PowerPoint didn't work, sorry. So the motivation. So what's a geoelectric field? A geoelectric field is an electric field that's induced on the surface of the Earth. This can usually happen between two primary methods, a solar flare, a big solar storm, or an EMP, or what we like to call a high-altitude EMP detonation. So these are usually caused by nuclear weapons detonated 30 kilometers or above in the atmosphere. They release lots of energy that interacts with the Earth's magnetic field and its own electromagnetic energy and couples into the grid that way. The fields drive these currents called geomagnetically induced currents. These currents are kind of completed the circuit between the electric grid and the Y-grounded transformers. So every so often in the power system, we'll have a big transformer, and it'll be Y-connected and it'll be grounded. And so the ground completes the circuit with the power lines. These currents have been known to cause large system power outages. The most famous one that you'll always see in literature, and it's quoted at task force meetings and things, is the 1989 Quebec storm. So it was pretty much the entire province of Quebec lost power for about 8 or 9 hours, which translated to like millions and millions of dollars lost, and I think a few people might have somehow unrelated probably gotten injured. There were sightings of high voltage transformers burning up. So what happens with these currents is that it creates hot spots in the transformers because it creates a megavar demand, a really high reactive power demand in the transformers. And so they start consuming all this extra energy that they're not meant to dissipate that much heat. And so it burns through the insulation and kind of causes some bad stuff to happen physically on the transformer. So what we're trying to do is to model these geoelectric fields better in a way that we can help power system operators respond to these type of events. There's been several storms kind of pop up over the last few years that I've been working on this. It's kind of interesting to go in and see the data and see the spikes and then go talk to the utilities and get their real data back, whether it's the magnetometers themselves or the GIC, the geomagnetically induced current CTs that they have to see the current spikes. And so correlating this data is something we're working really hard on right now. There's a few of us in Dr. Overby's group that are working on this phenomenon now. So it's kind of exciting. The research is a growing area, and I'm excited to be back working on it. Kevin? All right. Okay, so this electric field is defined between the magnetic field, which is H up here, the magnetic intensity, is defined by the impedance function Z. So the Z of omega is the impedance of the Earth. And what we're going to use is impedance at the surface of the Earth. Now, the Earth is made up of several different layers, going all the way down to the core, and each of these different layers can be broken down into different resistivity values. And so we're going to leverage work done by geologists and things to get those measurements of the different resistivities at the different levels so we can plug them into our model to get this impedance function Z. So the first part of this presentation is going to cover how to actually build this Z function so we can incorporate it into our electric field algorithm at the end. So like I was saying before, the Earth is made up of these different layers. So it's kind of, I found a good way to think about it is think of these layers as just a normal conductor, but now you have an almost DC-like signal, and that DC-like signal is the Earth's magnetic field changing very slowly. And so with the DC signal, your skim depth is going to go through the entire conductor. You're not going to just be on the surface of the conductor if you have a high-frequency signal or something. And so it's important to realize that this Z function, the impedance, is a function of the frequency. So the higher the frequency is, the less it's going to penetrate the Earth, which means it's not going to get into those other layers, so your overall impedance seen at the surface is going to be different. So it's important to make this realization that this analysis is based on the plane wave method. I don't know, a lot of people I think are taking, a lot of the new people are taking 520 now. Maybe y'all have covered that, I'm not sure. But it's kind of electromagnetic theory that says the waves propagating down happen in a plane. So everything is experiencing the same part of the wave at the same time. All right. So these are the models that we've been getting from the USGS, the Geological Society. They're 1D layered Earth models. So what that means is the Earth's conductivity changes as a function of depth, but not horizontally or vertically. So this divided up into these different regions, as you see here, in like everything in one of these candy caned coded regions is the same conductivity structure. So as you move to a different region, it is different. And so things that factor into that can be mountains, lakes, oceans, deserts, stuff like that. Over here, we see the actual conductivity as a function, or resistivity as a function of the depth. So you see how it changes as you get deeper. This is what's plugged into our models. So how do you actually go about calculating this? As you can imagine, you have all these layers on top of each other, and you're going to have a boundary condition at every layer between the two different media. And so you're going to have reflections going, the waves are going to reflect off the different surfaces, and the impedance is going to stack on top of each other. So as you calculate these layers, you start at the bottom layer, calculate the one above it in accordance with the boundary condition under it, and you keep going on top of that till you get to the very top of the surface. Once you get to the top, that value will take into account everything below it. This is the general equation. Here I have stop here for a one-layer model. That's an approximation of the layered Earth. If you just want to look at what happens if you have a one-layered Earth model, this is simply the intrinsic impedance, if anyone remembers that equation. So that's a very simplified version of this. But as you saw before, you can have 18 layers into the Earth to what we're going to model eventually. So here's another general form of the equation. And on the next slide, we'll actually go through what these different variables are and how I calculate it. So here's the calculation. You see familiar variables here like gamma, the reflection coefficient, lowercase gamma, the propagation constant, and eta, the intrinsic impedance. So a part of this approximation is that we're assuming mu is equal to mu naught. So that allows this equation to be much simplified like it is in this form as we go through the process. So like I said before, this process is repeated for each layer and it stacks on top of each other. Here's a single layer example, which this is the phase and the magnitude of it, which is what we'd kind of expect. So we have, this is just the intrinsic impedance of it for one layer, and we see the phase is constant at 45 degrees, which is what we'd expect. Could I have some water, please? And so we expect the phase to be constant. It's just the square root of imaginary numbers, so it's going to be 45 degrees. And it's not going to change as you scale the impedance. Thank you. All right. That's better. So you stop here after one layer, and you'll see here that I let the frequency range from 10 to the -6 to 10 to the 2. And that's because the phenomenon of the storm is that's how slow it varies. It doesn't vary at a high frequency rate, it goes very slow. So what happens when you go to a 3-layer example? So in 3 layers, you first calculate the bottom example, the bottom layer, and then you calculate the layer above that, and you'll see that incorporated into it is Z3, the impedance of the layer above it. And then for the next layer, do the same thing, you incorporate the one before that. So here's the fictitious Earth model I made up for this case. And then we'll see the plots on the next page. But you should think, what are these plots going to look like? We're going to expect them to have more action in it than just the constant phase and the exponential magnitude. So yeah, there's definitely some different stuff going on here, which is good. We're still analyzing this stuff, so it's stuff. So the cool thing is now we've actually modeled this Z function. This is something that we've been working on not for a long time, but it's something that's been in the back of our minds for several years now. And it's something that I'd probably encourage people to not shy away from things that in their research that they're scared of or they're intimidated by, because it's something that I put off for forever. I didn't want to get into the electromagnetics part of it. And then when I came back, Overby was like, let's look at this part of it. And I was like, oh, not again. Like, I've been down this road. I don't enjoy it. I don't want to do it. But I put on my grad school hat on, and like, it actually wasn't that bad. I knocked it out in a few weeks, and it's going to help everyone in our research group that's working on this stuff a lot. So it's really cool. So after we have the Z, now we can think about, okay, we need to fit a curve to this somehow, so we can get it back into that function of the electric field equals the Z, the impedance function, times the magnetic field. All right, so here's a 12-layer example. I was in Boston for the past little while, and so I chose to do the upper New England states here. And this is what the Earth model looks like. So I put these numbers into my algorithm, and this is what it spits out. So it's really nice to be able to do that instead of, like, I guess what I'm trying to say is it scales really nicely. Whether it's you put in 3 layers or 30 layers, it doesn't take long to calculate, and it helps with the accuracy of the algorithm. So now calculating the electric field. As we saw before, this is the equation right here that's key. And we're going to use some frequency analysis and some Fourier transform stuff in order to take advantage of the multiplication in the frequency domain, so we don't have to do recursive convolution in the time domain. Now, you can do recursive convolution in the time domain, but it's a bit tricky, and I didn't want to get into it. So I chose this easier way, and the recursive convolution in the time domain is something I'm going to investigate and help compare the results and see which is quicker and stuff like that. So that is how the EFT is calculated. So where does the magnetometer data come from that I've been talking about? So the magnetometer data is the h of omega, or it's actually h of t that I get, and I take the Fourier transform of that to get the h of omega. So this magnetometer data comes from public websites that publish real-time magnetometer data at usually NASA centers, or some utilities have magnetometers that they monitor and stuff like that also. So I get this data off the internet. For the longest time, it was a really big pain for me because I'd have to go to the website, I would copy this ugly HTML table, paste it in Excel, and then format it in Excel, and then paste it in a MATLAB matrix, and then run it. And so it was a big pain anytime I changed locations or the time of day of the storm or something. It was really painful. So I learned somewhat recently about web scrapers. How many people here are familiar with web scrapers or have heard the term? Okay, a lot of people have. That's good. And I thought it was interesting that I started to do this because I never would have done this had I not kind of taken a step back and said, how can I make my life easier and not just slave away at doing this? And so it's something I'd encourage people doing the research is, how can you leverage outside tools to help you make your research more efficient? Whether it's like computer science tricks, which I kind of consider this a computer science trick in a way, or something else. Maybe you're in the lab and you're soldering something. Maybe there's a special tool that you can buy that will help you solder stuff more efficiently or effectively. So I'm always a big fan of buy nice equipment, use nice things. It'll save you in the long run. So this is the HTML table I found online. Like I said, I was just dragging, copying, and pasting that. And then I built a web scraper, which is really just this top like 6 or 7 lines that has Java code in it. And then this is a parser that I built that parses it into a MATLAB matrix. So this is really just a function that's a part of my algorithm that takes in the Z data and spits out the E field. So here is an analysis of the storm I was talking about at the beginning in Quebec. This is the B field data. So this is the magnetic field data of the Earth and how it's changing over the length of the storm. To give you in kind of a ballpark, the magnitude of the Earth's magnetic field is about 50,000 nanoteslas. And so this is changing, on the order of 2,000 to 1,000. So that's like a 3,000 swing in the span of 24 hours. And so this is what causes the currents to flow in the grid that we don't want. These quick changes and oscillating back and forth, this is what does the damage. So I took the Quebec ground conductivity structure, put it in my algorithm with this. So these two are the inputs, and this is what it outputs. So this is the electric field in the x direction and the y direction, and this is the overall magnitude of it. This is something really rewarding in research that we probably all encounter is you run your code or whatever it is, and it finally compiles, and it spits out a graph that like you've seen before, and it looks familiar. And so this is really rewarding to see it match the real recordings of the electric field. And so, yeah, that was a really happy time. So in summary, I presented 2 algorithms, one for the geoelectric field, one for calculating the impedance function, and then a quick blurb on the web scraper and plug for finding tools that can help you do stuff faster. Here's some references, and I'd like to acknowledge ISEG. They are my funding. So thank you, ISEG. Yeah. Does anyone have any questions? Yeah.
Can you go to slide 15 or 16? Oh, all right. I was gonna say, have you thought about like buried cables in the ground? But you're never gonna bury a cable at 15 kilometers. I was thinking, like you can introduce that as another boundary condition. Like if you have a cable at a layer between 2 boundaries, it can be you model as a surface current instead of like a cable.
Yeah.
So it wouldn't just couple the power line, it would couple underground buried cables.
Yeah.
So I don't know.
That's a good point. So how we kind of approximate this in 2 different ways is the power lines are very close to the ground as compared to the electrojets in the Earth that are flowing around the atmosphere that are causing this to happen. So they're, hundreds, thousands of kilometers away from the Earth. And so whether the conductors are just under the surface or maybe just above the surface, the boundary of the air between the surface and the power lines isn't a factor in what we're doing. So
yeah, but I think if there's a conductor underneath, or I don't know, there's a wire flowing with 10,000 amps.
Yeah.
That would change the field. Right? There's
Yeah.
basically a source underneath. Like these layer models always assume a sourceless layer.
That's true. Yeah.
I don't know.
Yeah, that's a good point. Yeah. Cool. Shrikant?
The Earth is generally considered to be an equipotential surface, which we use as zero potential for all calculations, electromagnetic calculations. But this tends to imply that the potential is not really equal on the surface of the Earth. Is that because there seems to be shifting of potential because of the flow of current?
Yeah.
So is that really true that the potential
So when this research was first started back in the 80s-ish, actually even back in the early 60s, there's a little bit of research in this area. It was first modeled how the geomagnetically induced currents are calculated was called a Earth surface potential model. And that was actually used for maybe a decade or two before people realized that that was an inaccurate way to model it. I think it misrepresented the fact that this actual potential in the Earth doesn't change. It's the loop that's created by Faraday's law when you have a closed circuit between the conductors and the Earth that induces a source that's modeled in the actual power lines themselves. So, no, I don't think that it changes how we view the Earth as being equipotential.
And do you have any comments about the recent, maybe a month ago, there was a severe solar storm?
Yeah, so that was interesting because we heard from a few utilities as far down south as Missouri, and usually you get most magnetic activity near the poles, that they had a transformer, it was a generator trip due to high currents that were measured by a geomagnetically induced current sensor. And so they said, hey, we got this weird thing at trip. We measured these amps, and they sent us the data. He said, can you confirm this? Like, was it a storm? Like, what happened? And so that was right at the time where literally the day I just finished this stuff. And so I plugged in my data, and so I could pull the data, like the real-time data that just happened this past weekend, off online. At that point, I was still like copying and pasting. And I was able to view it, and it was really cool because we saw something similar like this, except like an order of magnitude smaller than this, actually. But there was a huge spike right at the hour that their generator tripped offline. And so it was like, whoa, which is cool because there's a lot of people out there that don't believe in this research in a way, if that makes sense. They kind of see this as a 1 in 100 year, 1 in 1,000 year thing that may not ever happen. But as we're getting more and more into this, as our group's getting more and more into this, we're finding more cases that are coming up that it's suggesting that this could be a more serious issue than a lot of us think it is. Yeah. Which slide, 11? Okay. Oh. Okay. Mm-hmm. Yeah. Yeah, so there's a few different ways to stop this current from entering into the grid. One of those ways is to put an impedance in line of the transformer grounding. So the most popular way that's kind of coming out to be what's the best way, what people are saying, is to put a capacitor in there. So it allows current to flow, it allows a certain current to flow and not another certain type of current to flow. And so it's really good for the grid. So it allows the AC to flow and not the DC to get through, because a DC capacitor in series blocks it, right? So the other way is putting a low ohmic resistor in. So this makes the current not want to go into the path of the transformer. But it's important not to put a high impedance resistor in there, because then you're going to have a grounding problem with your different stations. If you have a lightning strike or something like that, you need to make sure that the current, like the zero sequence current, and the unbalanced current can get out of the system. Yeah, that's a good insight, though. All right. Well, thank you, everybody. Yeah.
Dumb question.
That's something I need to look into more. But